Just come. This is working. Is the mic working? Hello? Okay. Is the mic working? Right. Hello, and you're welcome to the video. Okay, this is not a video, this is a live stream, and this is my first ever live stream on YouTube. So I hope this does well. Anyway, right. So what we're gonna be doing this live stream is I'm going to be following along with the Crafting Interpreter's book because I interested in building an interpreter, so I wanted to understand technologies involved in designing, building an interpreter. So in the future, we're going to be expanding on this to build other kind of, interpreter software. So we're gonna be doing things like compilers and all those kind of stuff. So we're gonna start from this building an interpreter's book. And from what I understand, this is divided into two sections. So here we have one that is written in Java, which is the tree walk interpreter. Then we have the bytecode virtual machine. So on this stream, we're going to be dealing with the tree walk interpreter. So we're going to start with this, and maybe on another stream, we're going to do the second one. So this one is written with Java and this one is written with C. So my plan for this is I'm going to follow the book and I'm going to use Java for this tree walk interpreter. And then when we're done, we're also going to implement the same thing here with C. And when we're done with the book and following every single tutorial or every single instruction on the book, and we understand how to properly build an interpreter, then we're going to rebuild that same thing in Zig. So that's my plan. Right. So we're going to start. Let's just get started. So welcome. This may be yeah, we're done with that. So let's move on to the next. Introduction. Right. Okay, yeah, we're going on a journey. This is really cool stuff. Okay, while I learn this stuff, please make sure you read these. Cool. Okay, okay. Oh, this is really great information. How this book is organized. Okay, yeah, we know three parts. Okay, this is the first part. Cool. Oh, we're talking about the code. All right. Oh, this is a nice picture. Right. Okay. We have cool snippets here. In case you're wondering, the book does not come with dark mode, so I'm using this dark reader. Yeah, it just hurts my eyes reading with light mode. So yeah. Um, right. Okay. This is right. So yeah. Okay. This is talking about the first interpreter. So this is JLox in Java. Yeah, we're focusing just on concepts and cool. As an aside, it's really been a while since I wrote any Java code. So hope I hope this goes real. Anyway, um, Yeah, it's really hard to come up with names for anything software development. Anyway, um, so let's see. We're done with that section. So we're gonna look at a map of the territory. So this is just talking about I believe. We don't want to wander all over the place. So before we set off, let's scan the territory charted by previous language implementers. Okay. This is probably useful information.
It's 4 o'clock.
All right. Thank you. It will help us understand where we are going and the alternate routes others have taken. First, let me establish a shorthand. Much of this book is about a language's implementation, which is distinct from the language itself in some sort of Platonic ideal form. Things like stack, bytecode, and recursive descent are not codes one particular implementation might use. From the user's perspective, as long as the resulting contraption faithfully follows the language specification, it's all implementation detail. Okay, I think that makes sense. We're going to spend a lot of time on those details, so if I have to write the language implementation, every time I mention them, I'll wear my fingers off. Okay, fair enough. Instead, I'll use language to refer to either a language or an implementation of it or both unless the distinction matters. The parts of a language. Engineers have been building programming languages since the dark ages of computing. As soon as we could talk to computers, we discovered doing so was too hard and we enlisted their help. I find it fascinating that even though today's machines are literally a million times faster and have orders of magnitude more storage, the way we build programming languages is virtually unchanged. Though the area explored by language designers is vast, the trails they've carved through it are few. Not every language takes the exact same path, some take a shortcut or two, but otherwise they are reassuringly similar from Ray Admiral Grace Hopper's first COBOL compiler all the way to some hot new transpiled to JavaScript language whose documentation consists entirely of a single poorly edited README in a Git repository somewhere. Okay, all right. So essentially, um, I see. The way languages are implemented is essentially the same. I think this is what we're trying to get from here. Okay, I think that makes sense. I visualize the network of path implementation. An implementation may choose as climbing a mountain. Start off at the bottom with the program as raw source text, literally just a string of characters. Each phase analyzes the program and transforms it to some higher level representation where the semantics, what the author wants the computer to do, becomes more. Okay. Eventually, we reach the peak. We have a bird's eye view of the user's program and can see what their code means. We begin our descent down the other side of the mountain. We transform this highest level representation down to successive lower level forms to get closer and closer to something we know how to make the CPU actually execute. Okay, so we're gonna start um, from the source code and then we're gonna scan it, try to understand exactly what the program is trying to do. So here we have, okay, we tokenize the. So I understand some concepts of interpreter and compiler development. So I understand some of these things like tokenization, parsing, syntax tree. I don't have like an in-depth knowledge of it, but yeah, I understand a few. So here we have analysis, optimizing. Okay, yeah. So we just this is for the tree walk interpreter, by the way. So we just do a syntax tree. Okay, this is a bit confusing for me. Um, I think this is broken down into like two, right? So we have the syntax tree parsing, which is what we're gonna be doing. I mean the three walk interpreter. So this is what we're gonna be doing in the stream. So I think it just goes from here all the way to here and to here. Hmm. Okay, all of this is probably related to the C implementation, and for the tree walk interpreter, I think we're just going to interpret the code as we parse or something. Okay, we'll see. Right. Let's trace through each of those trails and point of interest. Our journey begins on the left to the bare text of the user source code. Oh, this is explained. All right. So we have a variable average equals min plus max divided by 2, then scanning. So the first step is scanning, also known as lexing, or if you're trying to impress someone, lexical analysis. They all mean pretty much the same thing. I like lexing because it sounds like something an evil supervillain would do, but I'll use scanning because it seems to be marginally more complex. A scanner or lexer takes in the linear stream of characters and chunks them together into a series of something more akin to words. In programming languages, each of these words is called a token. Some tokens are single characters like open brackets, open brace, and comma. Others may be several characters long like numbers 1, 2, 3, string letters high, and identifiers min. Some characters in a source file don't actually mean anything. White space is often insignificant, and comments by definition are ignored by the language. The scanner usually discards these, leaving a clean sequence of meaningful tokens. Okay, so things like white space will just be stripped out of the original source code. So here we have like var average equals, then we have each of these is going to be broken down into meaningful tokens basically. Okay, I think this is pretty straightforward. And then we have parsing. Okay, so this is where our syntax gets a grammar, the ability to compose larger expressions and statements out of smaller parts. Did you ever diagram sentences in English class? If so, you've done what a parser does, except that English has thousands and thousands of keywords and an overflowing, whatever this is, cornucopia of ambiguity. Programming languages are much simpler. Parser takes the flat sequence of tokens and builds a tree structure that mirrors the nested nature of the grammar. These trees have a couple of different names, parse tree or abstract syntax tree. Okay. So an abstract syntax tree or a parse tree is simply the tokens that is built in a tree structure. Okay, so once we're done tokenizing, we just build a tree of those tokens, and that is what we call the AST or parse tree. Depending on how close to the bare syntactic structure of the source language they are. Okay. In practice, language hackers usually call them syntax trees, ASTs, or often just trees. Okay. Okay. This is like a binary expression. Max. Parsing has a long rich history in computer science that is closely tied to artificial intelligence community. Many of the techniques used today to parse programming languages were originally conceived to parse human languages by AI researchers who are trying to get computers to talk to us. Okay, I think some of these are just explaining some preliminary knowledge. I think these are useful, so I'm going to continue reading these, but I'm going to skip over some parts so that we can get to the code as quickly as possible because I think we have a lot to do on the stream, so I don't think we should spend too much time reading some of these things. But I know that these are valuable information, so I'm just going to um, read all this as fast as possible. The first two stages are pretty similar across all implementation. Now, the individual characteristics of each language starts coming into play. At this point, we know the syntactic structure of the code, things like which expressions are nested in which, but we don't know much more than that. In an expression like a plus b, we know we are adding a and b, but we don't know what those names refer to. Are they local variables, global? What are they defined? Where are they defined? The first bit of analysis that most languages do is called binding or resolution. For each identifier, we find out where the name is defined and wire the two together. This is where scope comes into play. The region of source code where a certain name can be used to refer to a certain declaration. If the language is statically typed, this is when we type check. Once we know where A and B are declared, we also figure out their types. Then, if those types don't support being added together, then we report a type error. Take a deep breath. We've attained the summit of mountain and a sweeping view of the user's program. Okay, so we've done tokenization and um, we've also done type checking, right? So all the semantic insight that is visible to us from analysis help needs to be stored somewhere. There are a few places we can squirrel it away. Often it's stored right back as attributes of the syntax tree itself, extra fields in the nodes that aren't initialized doesn't person but gets filled in later. Other times we may store data in a lookup table off to the side. Typically, the keys to these tables are identifiers, name of variables, and declarations. In this case, we call it a symbol table. Okay, and the value it associates with each key tell us what identifier refers to. The most powerful bookkeeping tool is to transform the tree into an entirely new data structure that more directly expresses the semantics of the code. Okay, this is the next section. Okay, so I think this is where we're doing the whole bytecode thing. So we compile the code to some bytecode that can be executed by the virtual machine. This is not what we're going to be doing on this stream because that would be like the next stream that we're going to be implementing in C. All right. Everything up to this point is considered the front end of the implementation. We might guess everything after this is the back end, but no. Back in the days of yore, when front end and back end were coined, compilers were much more simpler. Later, researchers invented new phases to stuff things between the two halves. All right. Rather than discard the old terms, William Wolf and company lobbed those new phases into the charming but spatially paradoxical name middle end. Okay, so now we have the front end, which is just Lexing, yeah, and building an AST, and now we have intermediate and backend. So intermediate representation, you can think of the compiler as a pipeline where each stage job is to organize the data representing the user's code in a way that makes the next stage simpler to implement. The front end of the pipeline is specific to the source language the program is written in. The backend is concerned with the final architecture where the program will run. Okay, so the front end is how we, take the specific language code, and convert it into some meaningful representation that we can then give to either the intermediate representation or the backend. So the backend is concerned with like the actual execution of the application. Okay, I think that makes sense. In the middle, the code may be stored in some intermediate representation. Oh, okay, this is the IR. So I think this is analogous to something like the LLVMIR, right? Um, so yeah, I think the LLVMR is a very good example. I think we have a bunch of other IR. So in Zig, we have something called the ZIR. Okay, so I think yeah. All right, cool. All right. Instead, the IR acts as an interface between these two languages. Okay, sorry, I think I missed something. That isn't tightly tied to either the source or destination forms, hence intermediate. Okay. So the IR acts as an interface between these two languages. This lets you support multiple source languages on target platforms with less effort. Say you want to implement Pascal, C, Fortran compilers, and you want to target x86, ARM, and Arduino Spark. Normally, that means you're signing up to write 9 full compilers: Pascal, x86, C, ARM, and every other combination. A shared intermediate representation reduces that dramatically. You write one frontend for each source language that produces the IR, then one backend for each target architecture. Now you can mix and match those to get every combination. That is really true. So what this is saying is, normally you would just write the front end and then lower the code to the back end for either execution or compilation. But if you have an intermediate representation, then you just develop that one front end and then one backend for each architecture. So x86, x86 64, and ARM, whatever the platform. Then you can use the generated intermediate representation to lower. So you use the IR to just lower the code directly, and it's quite straightforward. Hmm. And also, I think optimization is. Oh yeah, yeah. There's another reason. There's another big reason we might want to transform the code into a form that makes the semantics more apparent. Optimization. Before I continue, I'd like to let me just check to make sure that stream is still running. quality is big. Okay, I think this. So, all right, nice. So optimization, right? Once we understand what the user's program means, we're free to swap it out with a different program that has the same semantics but implements them more efficiently. We can optimize the code. Okay, that makes sense. Um, Simple example is constant folding. If some expression always evaluates to the exact same value, we can do the evaluation at compile time and replace the code for the expression with its result. So if the user types in this, okay, so the user, we have this expression, we could do all of the arithmetic in the compiler and change the code to okay, so this is like because we have constants here, everything is just going to be statically optimized, and then we're going to replace the we're just going to do this calculation while we're trying to compile the code, and then we're just going to put this here as the actual value. So, we've just done a very useful optimization because now we don't need to evaluate this expression anymore because yeah, it's a constant expression. Okay, I think that's why it's called constant folding. That makes a lot of sense. All right. Optimization is a huge part of the programming language business. Many language hackers spend their entire careers here, squeezing every drop of performance they can out of the compilers to get their benchmarks a fraction of a percent faster. It can become sort of an obsession. We're mostly going to help over that rat hole in this book. Many successful languages have surprisingly few compile time optimizations. For example, Lua and CPython generate relatively unoptimized code and focus most of their performance effort on the runtime. Hmm. Okay. So we have some aside. If you can't resist poking your foot into that hole, some keywords to get you started are constant propagation, common sub-expression elimination, loop invariant code motion, Jesus Christ, global variable numbering, strength reduction. What the All right, okay. Let's just leave this aside and continue with the actual we have applied all of the optimizations we can think of to the user's program. The last step is converting it to a form the machine can actually run. In other words, generating code. Where code here usually refers to the kind of primitive assembly-like instruction a CPU runs, and not the kind of source code a human might want to read. Okay, so this is code gen time. Code gen time. Want to actually start churning out some code. All right, let's do it. Finally, we are in the back end. So this is where the back end comes into play. Descending to the other side of the mountain. From here on out, our representation of the code becomes more and more primitive, like evolution running in reverse, as we get closer to something our simple-minded machine can understand. We have a decision to make. Do we generate instructions for a real CPU or a virtual one? If we generate real machine code, we get an executable that the OS can load directly onto the chip. Native code is lightning fast, but generating it is a lot of work. Today's architectures have piles of instructions, complex pipelines, and enough historical baggage to fill a 747 slugger page. Cool. Nice. Speaking the chips language also means your compiler starts with a specific architecture. If your compiler targets x86 machine code, it's not going to run on an ARM device. All the way back in the 60s, during the Cambrian explosion of computer architectures, that lack of portability was a real obstacle. To get around that, hackers like Martin Richards and Nicholas Worth of BCPL and Pascal fame respectively made their compilers produce virtual machine code. Instead of instructions for some real chip, they produce a code for a hypothetical idealized machine. Worth called this P code for portable, but today we generally call it bytecode because each instruction is often a single byte long. These synthetic instructions are designed to map a little more closely to the language's semantics and not be so tied to the peculiarities of any one compiler architecture and its accumulated historical craft. Hmm. You can think of it like a dense binary encoding of the language's low-level operations. Okay, so we're gonna be generating bytecode, which is just like machine code, but for a hypothetical machine that is going to be implemented by our own virtual machine. If your compiler produces bytecode, your work isn't over once that's done. Since there is no chip that speaks that bytecode, it's your job to translate. Again, you have two options. You can write a little mini compiler for each target architecture that converts that bytecode to native code for that machine. You still have to do work for each chip you support, but this last stage is pretty simple and you get to reuse the rest of the compiler pipeline across all of the machines you support. You're basically using your bytecode as an intermediate representation. Yeah, I was gonna say that. So this is the same as just having like an IR. You know, if your bytecode is going to be compiled to the target machine code, then you're just building then your bytecode is just an intermediate representation. All right. Or you can write a virtual machine, a program that emulates a hypothetical chip supporting your virtual architecture at runtime. Running bytecode in a VM is slower than translating it to native code ahead of time because every instruction must be simulated at runtime each time it executes. In return, you get simplicity and portability. Implement your VM in, say, C, and you can run your language on any platform that has a C compiler. This is how the second interpreter we build in this book works. Yes, so the second interpreter we're gonna do it with C. Nice. Um, okay. Runtime. We finally hammered the user's program into a form we can execute. The last step is running it. If we compiled it to machine code, we simply tell the operating system to load the executable and off it goes. If we compiled it to bytecode, we need to start up the VM and load the program onto that. In both cases, for all but the basis of low-level languages, we usually need some services that our language provides while the program is running. For example, if the language automatically manages memory, we need a garbage collector going in order to reclaim unused bits. If our language supports instance of tests, so you can see what kind of object you have, then we need some representation to keep track of the type of each object during execution. I think this is RTTI. All this stuff is going at runtime, so it's called appropriately the runtime. In a fully compiled language, the code implemented in runtime gets inserted directly into the resulting executable. In say Go, each compiled application has its own copy of Go's runtime directly embedded in it. If the language is run inside an interpreter or VM, then the runtime lives there. This is how most implementation of languages like Java, Python, and JavaScript works. Shortcuts and alternate route. That's the long path covering every possible phase you might implement. Many languages do walk the entire route, but there are a few shortcuts and alternate paths. Okay, so if we don't want to do all of this work, let's see, single pass compilers. Some simple compilers interleave parsing, analysis, and code generation so that they produce output code directly in the parser without ever allocating any syntax trees or other IR. Okay? These single pass compilers restrict the design of the language. You have no intermediate data structures to store global information about the program, and you don't revisit any previously parts of the code. That means as soon as you see some expression, you need to know enough to correctly compile it. Pascal and C were designed around this limitation. At the time, memory was so precious that a compiler might not even be able to hold an entire source file in memory, much less the whole program. Okay, that explains why C is, well, amazing. This is why Pascal's grammar requires type declaration to appear first in a block. Oh, this is why in C you can't call a function above the code that defines it unless you have an explicit forward declaration that tells the compiler what it needs to know to generate code for a call that to the later function. Okay, all right, this makes a lot of sense. We had, technical limitations in the past, and so yeah, that's why all these languages are implemented the way they were. All right. So we have three work interpreters. Some programming languages begin executing code right after parsing it to an AST, maybe a bit of static analysis applied. To run the program, the interpreter traverses the syntax tree, one branch, blah blah blah. This is like, yeah, three work interpreters. We're just trying to. This implementation style is common for student projects and little languages, but it's not widely used for general purpose languages since it tends to be slow. Some people use interpreter to mean only these kinds of implementations, but others define the word more generally. So I'll use the inarguably explicit tree walk interpreter to refer to these. Our first interpreter rolls this way. So we're going to be building the slow one, you know, in this stream. And then we're going to move to doing actual with C. So, Java is inherently so on the C, but then we're going to be building our own virtual machine in the next stream. And yeah, we're also going to be using the same code. Anyway, so transpilers. Writing a complete backend for a language can be a lot of work. If you have some existing generic IR to target, you could bolt your front end to that. Oh, this is like an LLVM thing. Otherwise, it seems like you're stuck. But what if you treated some other source language as if it were an intermediate representation? Oh, this is like compiling to say C, and then you use the C compiler to compile the code to the actual machine or the actual machine that you're targeting. You write a front end for your language, then in the back end, instead of doing all the work to lower the semantics to some primitive target language, you produce a string of valid source code for some other language that's about as high level as yours. Then you use the existing compilation tools for that language as your escape route off the mountain and down to something you can execute. I think this makes a lot of sense if you're just starting out to build a language. I think it makes sense to start with like a transpiler, and you just have like your target be C because it's easy to build, to lower your code to compile to C. And then as your language matures, you can actually start looking at compiling your code to be to have a native target basically. um yeah, but then at least you can get instant results because C is a language that actually works, and it has lots of support for almost every possible CPU out there. So if you compile your code to C, then you can target those CPUs. And then as your language matures and you now have time to, actually maybe compile for write your backend code for those targets, then you can ditch C, and or you can just keep C as one of the backends. I think that makes sense. They used to call this a source to source compiler or transcompiler. After the rise of languages that compile to JavaScript in order to run in the browser, they've affected the hipster subrequest transpiler. While the first transcompiler translated one assembly language to another, today most transpiler work can translate in high-level languages. After the viral spread of Unix to machines various and sundry, they began a long tradition of compiler blah 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 blah. Okay, this is really cool. Web browsers on the machine, blah 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 blah. Okay, this is really cool. Yeah, we fully understand what this is saying. But so okay, this is just talking about transpilation, so I think we can just skip it. And then it's talking about just in time compilation. So yeah, this is like when you just compile code as yeah, it just compile code. I think it has something to do with like as you're interpreting the code, then you're going to determine whether you should compile some hotspot, some frequently run parts of the code into machine code, and because of that, it makes the execution of the code faster. Anyway, so here we have compilers and interpreter. So what is the difference between a compiler and interpreter? Um, Turns out this is like asking the difference between a fruit and a vegetable. That seems like a binary either or choice, but actually, fruit is a botanical name, and vegetable is culinary. One does not strictly imply the negation of the other. There are fruits that aren't vegetables and vegetables that aren't fruits, but also edible plants that are both fruits and vegetables, like tomatoes. So, back to languages. Compiling is an implementation technique that involves translating a source language to some other, usually lower level form. When you generate bytecode or machine code, you are compiling. When you transpile to another high level language, you are also compiling. Okay, that makes sense. When we say a language implementation is a compiler, we mean that it translates source code to some other form but does not execute it. The user has to take the resulting output and run it themselves. Conversely, when we say an implementation is an interpreter, we mean it takes in source code and executes it immediately. It runs programs from source. Yeah, okay, this makes sense. Like apples and oranges, some implementations are clearly compilers and not interpreters. GCC and Clang take your C code and compile it to machine code. An end user runs that executable directly and may never even know which tool was used to compile it, so these are compiler for C. In older versions of Math's canonical implementation of Ruby, the user ran Ruby from source. The implementation parsed it and executed directly by traversing the syntax tree. No other translation occurred, either internally or in any user visible form, so this was definitely an interpreter for Ruby. But what of CPython? When you run your Python program using it, the code is parsed and converted to an internal bytecode format, which is then executed inside the VM. From the user's perspective, this is clearly an interpreter. They run their program from source, but if you look on the CPython scaly skin, you see that there's definitely some compilation going. Right, okay. The answer is that it is both. CPython is an interpreter and it has a compiler. In practice, most scripting languages work this way, as you can see. Okay, so TypeScript is strictly a compiler, Rust, Clang, yeah, this makes a lot of sense. All right, read JLogs. Also, JLogs that we're going to be building here is actually just an interpreter. And then we have C Sharp, Pascal, CLogs. This is going to be the C version of this, and this is actually a compiler and an interpreter. This is really cool. That overlapping region in the center is where our second interpreter lives too, since it internally compiles to byte. So while this book is nominally about interpreters, we'll cover some compilation too. Okay, all right, that's cool. Let's just move straight to the Lux language. All right. Um, we'll spend the rest of this book eliminating every dark, sundry corner of the Lux language, but it seems cruel to have you immediately start grinding out code for the interpreter without at least a glimpse of what we're gonna end up with. At the same time, I don't want to drag you through reams of language lawyering and specification as before we get to touch your text editor. So this will be a gentle, friendly introduction to logs. It will leave out a lot of detail on edge cases. We got plenty of time for those later. This is now where we get into the actual language. So let's take a look. Um, Here we have comments, really cool, C style comments, and then we have print. Interestingly enough, this print is not a function, so I'm thinking this is like a built-in thing. Okay, so we understand that we don't need to- let's just scroll. Of course, this is dynamic typing, so this means Lux is dynamically typed. Variables can store values of any type, and a single variable can even store values of different types at different times. If you try to perform an operation on values of the wrong type, say dividing a number by a string, then the error is detected and reported at runtime. Okay. There are plenty of reasons to like static types, but they don't outweigh the pragmatic reason to pick dynamic type for logs. A static type system is a ton of work to learn and implement. Skipping it gives you a simpler language and a shorter book. We'll get our interpreter up and executing bits of code sooner if we defer our type checking to runtime. Okay, that is fair. That is really fair. Um, Automatic memory management. Yeah, so we're gonna be doing garbage collection. Garbage collection. I think we have garbage collection and reference counting. So in this case, we're gonna be doing garbage. Okay, so we have data types. Let's go. We have booleans, true or false. We have numbers. And okay, logs has only one kind of number, double precision floating point. Okay, so we're gonna be using double doubles for both integers and floating point numbers. Let's go. We have strings. Really cool. Hmm. So there's quite some complexity hiding in that innocent sequence of characters. Then we have nil. Hmm. Represents no value. It's called null in many other languages. Logs we spell it nil. Really cool. I love the fact that we're using the name nil and not null. Right. When we get to implementing it, this will help distinguish when we're talking about Lux's new value versus Java's or C's null. All right. There are good arguments for not having a null value in a language since null pointer errors are the scourge of our industry. If we were doing a statically typed language, it would be worth trying to ban it. In a dynamically typed one, though, eliminating it is often more annoying than having it. Okay, expressions. If built-in data types and the literals are atoms, then expressions must be the molecules. Most of these will be familiar. Alright, so we have arithmetic expression, we can add, we can subtract, we can multiply, we can divide, cool stuff. We can also do some negation. Makes a lot of sense. We have comparison operators. Yeah, comparison, and comparisons. Yeah, I'm against implicit conversions too because JavaScript just sucks. Anyway, logical operators. So yeah, so this is like negation. So we can negate true and it gives us false. We can negate false and it gives us true. This is making sense. True and false, true and true. Yeah, this is like, so you're trying to, this is like checking if the left hand side expression evaluates to true and the right hand side evaluates to true. In this case, they both evaluate to true, so we get true. The and is the operator here. All right. And then we also have an or operator, which either one of these should be true. If both of them is false, then you get false as a result. This is making sense. Right. So we have um precedence, operator precedence. All of these operators have the same precedence and associativity that you'd expect coming from C. When we get to parsing, we get way more precise about that. In cases where the precedence isn't what you want, we can use this to group stuff. So we can use parentheses to group expressions, and yeah, the parentheses take more precedence than whatever else we're trying to evaluate. That makes a lot of sense. Since they aren't very technically interesting, I've cut the remainder of the typical operator manageri out of our little language. No bitwise, shift, modulo, or conditional operators. I'm not grading you, but you will get bonus points in my heart if you augment your own with them. Okay, I don't think this should be quite difficult to implement since we already have some basic, right? So we can just figure out how the rest is done once we have those basic operators set up. Um, yeah, those are the expression forms, except for a couple related to specific features that we're going to. Let's move up. All right, statements. So we have statement. Statements are terminated a semicolon. Have an expression like this, right? We have a block. Yeah, so scoping. All right, and we have variables. So you declare variables using var statements. If you omit the initializer, the variable's value defaults to nil. Okay, so you can do these things just as we do it in JavaScript. And the value is new. Once declared, you can naturally access and assign a variable using its name. So var, that's fine. Okay. There is one thing that I think has not been shown, and I think it's probably like variable declaration. So we're just doing mutable variables here. We don't have constants, so okay. It's hard to write useful programs if you can't skip some code or execute some modern ones. That means control flow. Okay. So this is a control flow and while loops, if else statements, we have for loops. This is looking good. We have functions. Yeah. So we can call functions with arguments. This is really cool. You can also call a function without passing anything to it. Unlike in say Ruby, the parentheses are mandatory in this case. If you leave them off, the name doesn't call the function, it just refers to it. Language isn't very fun if you can define your own functions. In logs, you do that with fun. Nice. Print some, take A and B, print that. Now is a good time to clarify some terminology. Some people throw around parameters and argument like they're interchangeable, and to many they are. We're going to spend a lot of time splitting the finest of Downey hairs around semantics, so let's sharpen the word. From here on out, an argument is an actual value you pass to a function when you call it. So a function call has an argument list. Sometimes you hear actual parameters used for this. Actual parameter, okay. The parameter is a variable that holds the value of the argument inside the body of the function. Thus, a function declaration has a parameter list. Others call these formal parameters or simply form. This is very confusing because this reads like we're still talking about the same thing, right? These are parameters. And when you call the function, you're passing the um these these are arguments, I believe. These are parameters. Okay, let's just continue with this. The body of a function is always a block. Inside it, you can return a value using a return statement, just like that. If execution reaches the end of the block without hitting a return, it implicitly returns nil. Okay, so we have closures. Functions are first class in logs, which means functions are first class in logs, which just means there are real values that you can get a reference to storing variables pass around. So, okay. Oh, this is really cool. So we can actually pass a function into a function. Wow. That is nuts. That is crazy. Wow, that's amazing. Since function declarations are statements, so this will allow us to build crazy things in function approach. We can declare looking functions inside another function. So we have looking function. Okay, looking good. If you combine local functions, first class functions, and block scope, you run into this interesting situation. Yeah, of course, where you have an outer variable, then inside the inner function, you're referencing the outer variable here. Here, inner accesses the local variable declared outside its body in surrounding function. Is this kosher? Now that lots of languages have borrowed this feature from Lisp, you probably know the answer is yes. For that to work, inner has to hold on to references to any surrounding variables that it uses so that they stay around even after the outer function has returned. We call functions that do this closures. These days, the term is often used for any first-class function, though it's sort of a misnomer if the function doesn't happen to close over any variables. As you can imagine, implementing these had some complexity because we can no longer assume the variable scope works strictly like a stack, where local variables evaporate the moment the function returns. We're gonna have fun time learning how to make these work correctly and efficiently. Oh, goodness. Okay. Now we have classes, of course. Okay, and this is object oriented, so you can extend this. All right. Yeah, I prefer classes to prototypes, to be honest. Yeah, classes and logs. All right. Class, we functions and members of the class, and can can pass a class itself. Oh, that's crazy. Hmm. Class is a first class. Okay. This looks similar to JavaScript classes though. Right, I think it does. Yeah, it definitely does. Um, can pass. We can store the object in a variable. Hmm. Oh, this is storing the actual class instance, not an instance of the class, the actual class itself. Hmm. Okay, so instances of a class is denoted with this parenthesis. This is when you actually construct the instance of a class. All right, makes sense. All right, instantiation and initialization. Yeah, breakfast of meat, breakfast of bread. So we're going to be adding fields. So we can freely add values, add properties to our class. Okay, I have to admit that is, well, that is cool since this is a dynamically typed language. Um, if you want to access a field or method on the current object from within a method, use the good old this, of course, of course. Um, okay, so we have an init. This is a constructor. So whenever every time we try to create an instance of this, then we're gonna get. All right, cool. And then we have inheritance. So we have extending stuff. That okay, okay. So we use this less than for extension. We can also call super class constructors. Okay, okay, not bad. Now standard library. Yeah, I know there's no standard library. Just clock. Okay, not bad. I think we already have more than enough to actually attempt to build a standard library, so it's okay if we just skip that part. Now let's start writing some code down. Right. So scanning. Should we read this? I don't think so. Yeah, take big bites. Anything we're doing is what overdoing. I really like these codes. I have absolutely no idea what this means, but I love it. Right. Yeah. The first step in any compiler or interpreter is scanning. The scanner takes in raw source code as a series of characters and groups it into a series of chunks we call tokens. These are the meaningful words and punctuations that make up the language's grammar. Scanning is a good starting point for us too because the code isn't very hard. Pretty much a switch statement with delusions of grandeur, right? It will help us warm up before we tackle some of the more interesting material later. By the end of this chapter, we'll have a full featured fast scanner that can take any string of log source code and produce the tokens that will feed into the parser in this chapter. Now we have the interpreter framework. All right. Since this is our first real chapter, before we get to actually starting some code, we need to sketch out the basic shape of our interpreter, JLogs. Everything starts with a class in Java. Yeah, of course. Now we need to create our project. So what I'm going to do is I'm going to hop over to IntelliJ. I'm going to be using IntelliJ. I'm going to create a new project. This is going to be JLogs. Yep. We're going to be using Java. It would be tempting to actually use Kotlin because I think Kotlin is a better language, in my opinion, especially because I only know my Java knowledge is only limited up to um my Java knowledge is limited to Java 8. So yes, I have a fairly old knowledge of Java, and Kotlin would be a more appropriate language to use, but I want to stick to the book as much as possible, so we're just gonna use Java. And the build system is gonna be Gradle, Gradle DSL. I'm gonna use Kotlin for DSL. Yeah, let's just leave everything else as is. What do we have? Oh yeah, we're gonna leave everything, and I'm gonna hit create. And here, okay, what's that? And now I have to wait for Gradle to download. Of course, of course. Oh goodness. Okay, looks like it's done with the download, so we can start writing some code. What's this? Um, oh, none of these things work. Okay. Well, we have to wait for this to finish doing whatever the hell it's doing. Um, let me try to see if I can. Okay. All right. I think the audio sounds nice. Um, okay. All right. Cool. Here now we are done. We can start writing some code. And here we can see that we have a locks class. The package name is going to be different because, of course, I have a different package name here, but yeah, let's just create the class. So we have locks.java. I'm gonna create the file locks, and here we have our locks class. So the first thing we do is we have our main function. Okay, that means that I have to delete this one because locks is going to be our main class, right? And we have public static void main, just as we have here, but in this case, this throws an IO exception. So let's make sure to do that here. And now we're trying to parse some arguments. If so, length is less than, it's greater than 1. Oh, so this is where we actually and usage jlogs script. Okay, yeah, we're gonna use scripts like this. That's why they're on. And then system.exit 64. Else if args.length equals 1. So if it is run file args at 0, right? Then run prompt. Okay, so from what I see, I think this is going to run the actual this is going to, so if our args.length is 1, we're going to take that as a file path and we're going to interpret the code inside of the file. And if we just have more than one argument, then we've used the input or prompt wrong, and so we're just going to print the usage and exit. And here, if we don't pass in any argument and we just run the code, then we're going to hit this run prompt function. Okay, makes perfect sense. So yeah, it executes directly from source, whatever, and then we're gonna do the run file function. So private static void run file. It looks like this is going to be running a loop. String path IO exception. And here we're gonna make byte have bytes. We're gonna do files.read all bytes. Okay. This is going to be the path. So we're essentially just reading the contents of whatever path that was given to us here into a byte array. And this is what we're going to be using. So this is our source code basically, and that's what we're going to be tokenizing and parsing. Let's go. And we also have another function that we have to implement. And here we have a new string. It's char set. We need to pass in a char set. That's interesting. Anyway, now we have another function to implement. Okay. And we have the run prompt. So the run prompt is this one that we're going to execute when we don't have any argument passed into the program. So it's going to be like it's going to be an interactive shell basically, where you can define variables and run your code interactively. I keep forgetting the name that it's called. Anyway, this is not Kotlin, so stop doing fun. Yeah, we're gonna run the prompt. And here we're gonna do, okay, this also is going to throw your exception. So we build an input stream reader from the system in, okay, and then we turned out to a buffered reader, right? And then we're going to do a buffered there. Are goes to new buffer reader. We pass that into it. Let me just get this out. And now we're going to have an infinite loop. Interesting. So, and for this, we're going to print out a prompt string. On the same line, we're going to run a read line. Line is null, we break. All right. So this is going to be system out print. We have a prompt string like this, and well, so we're going to do string line read line, and yeah, we need to check if line is null. Okay, line, if line is null, we're gonna break. If not, we're gonna call that imaginary run function and pass in the line. So I think run is going to be responsible for the actual tokenization, because at the moment I see that, you know, we have so run file is going to read the string from a file and it's going to pass it into the run function. Here we're also getting the data, which is the code from standard in, and we're also putting that in the run function here. So yeah, that is making sense. Okay, so the readline function, yeah, we know. Also, when we press Control D, it's going to signal an end of file, and we're gonna get null. So we're gonna use that to exit this loop. I think that makes a lot of sense. Both the prompt and file runner are throwing repels around this core function. Yeah, run. So let's do it. Private static run string. What am I gonna call it? Source code. Yeah. Should this throw IO exception? No. So we're building a scanner out of this. Let me see. This is going to scan the source code. This is going to get the tokens. The scanner that we have here, I don't think this is a Java util scanner, right? Because we have scan tokens, and I know that the Java util scanner does not have this function, so we're gonna have to create this class. And then it's just going to print out the tokens for now. Okay, let's do it. Scan equals new scanner. We're gonna pass the source code. List of tokens is going to be equal to scan tokens. So we need to create two new classes, scanner and token, all right? And then we're just gonna print it out, okay? Token, gonna do token, yes. Yeah, okay, looks good. Now, yeah, we haven't written the interpreter problem. So we're dealing with error handling next. So let's just hop straight to the code. So what are we doing here? We say, okay, we're gonna report an error, and we're gonna specify the line and the message. Okay, let's do it. This is going to be a start error. It's line string message. And what we're gonna do here is call the report function just as this is implemented. Line message. Okay. So we have a private static void report, and we're just going to store. We also have a static variable here called had error. Interesting. Right. So static port line string there string message. So this is for error reporting, I believe. And so what we're gonna do is print to the system error. Okay. Line okay. Error. Yeah, I think we need to put like a space in here. Where a colon plus message. Okay. Yeah, I think this makes a lot of sense. Oh yeah. Error where specify the message. All right. What is this? Get out. And then we need to do a flag. I think we probably need to store that flag here. Boolean had error. Here we're gonna set that had error to true. Okay, so this error function and its report helper tells the user some syntax error occurred on a given line. That is really the bare minimum to be able to claim you even have error reporting. Imagine if you accidentally left a dangling comma in some function call and the interpreter printed out error, unexpected comma somewhere in your code. Good luck finding. Okay, that's fair. That's not very helpful. We need to at least point them to the right line. Even better would be the beginning and end column so they know where in the line. But even better than that is to show the user the offending line, like, yeah, okay, this is something like Rust. I'd love to implement something like that in this book, but the honest truth is that's a lot of grungy string manipulation code. Very useful for users, but not super fun to read in a book and not very technically interesting. So we'll stick with just a line number in your own interpreters. Please do as I say and not as I do. Okay. We're not gonna do that. We're gonna do exactly as you do in this, right? The primary reason we're sticking this error reporting function in the main logs class is because of the hard error field. It is defined here. Okay. Ours is private. His is not private. We use this to ensure we don't try to execute code that has a known error. Also, it lets us exit with a non-zero exit code like a good command line citizen should. Okay. Okay. So this happens in, I think, run file and in run prompt. So we're gonna add that. And in run file, we're just gonna check if had error system the exit 65. And we're gonna do, oh, it says we need to reset this flag in the interactive loop. If the user makes a mistake, it shouldn't kill their entire session. So, okay. That means that for our run prompt, okay, so that means that we're going to reset this in case we have like some syntax error from the user or something. All right. The other reason I pulled the error reporting out of here instead of stuffing into the scanner and other phases where the error might occur is to remind you that it's good engineering practice to separate the code that generates the errors from the code that reports them. Various phases of the front end will detect errors, but it's not really their job to know how to present that to a user. In a full-featured language implementation, you will likely have multiple ways errors get displayed. On std_error, in an IDE's error window, log to a file etc. You don't want that code smeared all over your scanner and parser. That's true. Ideally, we would have an actual abstraction, some kind of error reporter interface that gets passed to the scanner and parser so that we can swap out the different reporting strategies. For our simple interpreter here, I didn't do that, but I did at least move the code for error reporting into a different class. Okay, yeah, I think it makes sense. So normally we would have like a class that abstracts, the error reporting stuff, but yeah, okay. With some rudimentary error handling in place, our application shell is ready. Once we have a scanner class with a scan tokens method, we can start running it. Okay. Before we get to that, let's get more precise and yeah, okay. About what? Excuse me. Before we get to that, let's get more precise about what tokens are. Okay, lexemes and tokens. Here is a line of logs code. Var language equals logs. Here, var is the keyword for declaring a variable. That three character sequence var means something. But if we yank 3 letters out of the middle of the language, like gua, gua, those don't mean anything on their own. That is what lexical analysis is about. Our job is to scan through the list of characters and group them together into the smallest sequence that still represents something. Each of these blobs of characters is called a lexeme. In that example line of code, the lexemes are, yeah, so it's broken down into like 1, 2, 3, 4, 5. Yeah, we have 5 tokens. The lexemes are only the raw substrings of the source code. However, in the process of grouping character sequences into lexemes, we also stumble upon some other useful information. When we take the lexeme and bundle it together with that other data, the result is a token. It includes useful stuff like token type. Keywords are part of the shape of the language's grammar, so the parser often has code like, if the next token is while, then do. That means the parser wants to know not just that it has a lexeme for some identifier, but that it has a reserved word and which keyword it is. The parser could categorize tokens from the raw lexeme by comparing strings, but that is slow and kind of ugly. Instead, at the point that we recognize a lexeme, we also remember which kind of lexeme it represents. We have a different type for each keyword. Operator, bit of punctuation, and literal type. All right, so we need to create a new token type class. Let's do it. This is going to be an enum. So let's just do public enum token type, and so we have single character tokens, and this is going to be a left parenthesis, a right parenthesis, left brace, right brace, we have comma, dot, minus, plus, semicolons, slash, star. This is a forward slash, I suppose. Okay, now we have one or two character tokens. Okay, looking good. Bang and bang pause. Okay, this is like the equals and not equals operators. Equals, yeah, not equals or negation operator. Equal, 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 greater, greater, equal. Here we have less, less, equal. What are the operators? So we now have literals. And literals are string literals. Basically, we have identifier strings and numbers. Okay. So I think identifiers are simply something like a name of a variable. Is going to be an identifier in this case. Another literal we can have is going to be the class name. So we have like some sort of class like breakfast. So breakfast is going to be an identifier in this case. It represents the name of a class, but it is an identifier. We know what strings are. Strings are just going to be things that are inside of quotes, and numbers are number literals like 39, 40. So I think that makes sense. And then we have keywords. So keywords are the actual reserved words that we use in the language. So this makes a lot of sense. Keywords, and class else false on or if nil or print return per is true for while var while. Okay, and then at the end we have the end of file. I believe that this is just a marker to say, hey, we're done, and you shouldn't do anything else. Okay. The lexeme for literal values, numbers and strings and the like. Since this scanner has to walk each character in the literal to correctly identify it, it can also convert that textual representation of a value to the living runtime object that will be used by the interpreter later. Okay, so this class is just there to tell us what kind of token we're dealing with. Oh, okay, looks good. Now, location information. Back when I was preaching the gospel about error handling, we saw that we need to tell users where errors occurred. Tracking that starts here. In our simple interpreter, we note only which line the token appears on, but more sophisticated implementations inside the column and len too. We take all of this data and wrap it in a class. So this is going to be a token class that takes in the information about what kind of token, the actual value of the token, yeah, the line number that the token existed on. Okay. Right, so let's do that. Let's create a token class. Token. Here we go. And now, so we have 4 fields, token types. Let's do that. Type, token type. Just gonna call it type. Final string lexeme. I believe the lexeme is the actual string value, as we get it from the source code, right? And then object literal. So the literal is simply the the value. So in this case, remember that we talked about having literals here, and we have identifier, string, and number. So in this case, for the literal, I think we're gonna have the string and the number, or the identifier. I think the lexeme should store the value for the identifier. So anyway, we're gonna find out. And then we have line. Cool. Let's build ourselves a constructor, just like that. We seem to have a problem. Okay, yeah, this is fine. So now we can properly, we now have our token here. We still don't have our scanner class, but we'll get to that. And let's do a toString, probably string to. It's not like a toString. Okay. Then we could turn types lexeme. Okay. Um. Okay. Space plus literal. So this is, yeah, whenever we try to print this token, this is what we're gonna get. All right. Now we have an object with enough structure to be useful for all of the later phases of the interpreter. So regular languages and expressions. Now that we know what we're trying to produce, let's, well, produce it. The core of the scanner is a loop. Starting at the first character of the source code, the scanner figures out what lexeme the character belongs to and consumes it and any following characters that are part of that lexeme. When it reaches the end of that lexeme, it emits a token. Then it loops back and does it again, starting from the very next character in the source code. It keeps doing that, eating characters and occasionally excreting tokens until it reaches the end of the input. Okay, that makes a lot of sense. Um, the part of the loop where we look at a handful of characters to figure out what kind of lexeme it matches may sound familiar. If you know regular expressions, you might consider defining a regex for each kind of lexeme and using those to match characters. For example, Lux has the same rules as C for identifiers and the like. This regex matches one. I think it might be. Hmm. I really don't like to use regular expressions to parse source code, right? I think error handling might be a bit difficult to do with that. But I might be wrong. Yeah. If you did think of regular expressions, your intuition is a deep one. The rules that determine how a particular language groups characters into lexemes are called its lexical grammar. In logs, as in most programming languages, the rules of that grammar are simple enough for the language to be classified as a regular language. That's the same regular, whatever, blah, blah. You very precisely can recognize all of the different lexemes for logs using regexes if you want to. And there's a pile of interesting theory underlying why that is and what it means. Tools like Lex or Flex are designed expressly to let you do this. Throw a handful of regexes at them and they give you a complete scanner back. Since our goal is to understand how a scanner does what it does, we won't be delegating that task. We're about handcrafted goods. Yes, let's go, baby. Let's go. Yeah, so the scanner class. Without further ado, let's make ourselves a scanner. Let's do it. Let's do it. Need to make that scanner, man. So we're gonna do scanner class. And here we're going to have two fields here, source code and a list of tokens. Okay, private final string source and private list of token is new array lists. And there we go. Okay, this has to be like final. We're gonna make a constructor string source. Star source is source. Typical Java stuff. Yeah, we store the raw source code as a simple string, and we have a list ready to fill with tokens we're going to generate. The aforementioned loop that contains that looks like that. This. Okay, so this is a function. All right. Of tokens, scan tokens. My question is, why does it have to return that? Oh, I see. Okay. When do we delete these tokens though? Okay, I think we don't. We just keep, so every time scan tokens is called, we just append the new tokens here. Okay, looks good. Let's go. While not it's at end. Okay. We are at the beginning of the next lexeme, so start is current. Scan token. Dot add new token. And we need the token type. And this is going to be, so we're adding an end of file token basically. The lexeme is empty, the object literal is null, and the line is like these variables we don't have at the moment, but that's fine. We're gonna get to it. The scanner works its way through the source code, adding tokens until it runs out of characters. Then it appends one final end of file token that isn't strictly needed, but it makes our parser a little cleaner. This loop depends on a couple of fields to keep track of where the scanner is in the source. Okay, so let's do it. We need start current online. So start row private row private. Okay, looks good. The start and current fields are offsets that index into the string. Okay, so there, yeah, okay. The start field points to the first character in the lexeme being scanned, and current points at the character currently being considered. Okay. The line field tracks what source line current is on, so we can produce tokens that know their location. Then we have one little helper function that tells us if we've consumed all the characters. Okay, so it's at end. All right. Boolean. Oh yeah, I forgot to return tokens here. Is at end. This is going to return current is greater than or equal to source.length. Right? Yeah. Recognizing lexemes. All right. This is where we actually start doing the tokenization. So let's see how it goes. In each turn of the loop, we scan a single token. This is the real heart of the scanner. We'll start simple. Imagine if every lexeme were only a single character long. All you would need to do is consume the next character and pick a token type for it. Several lexemes are only a single character in log, so let's start with those. Okay, so we're gonna start parsing the single characters. Let's do it. And private void scan token. Alright. Okay, so we need the next character. And so we call advanced to give us the next character. And then we switch on that character. So we start looking at the single character tokens. Or add token. This is token type. C's and break. And we're gonna do same for the right parentheses. And we're gonna do for the left brace. Nice. We're gonna do for the right brace. We're gonna do comma dots. Okay. Then we have minus. What else? Plus semicolon star. Okay. It's plus semicolon. Have the asterisk star. Okay, this is looking good. So these are single characters that we have in the language. This isn't done yet, I think. But let's just define our help parameters as we follow along the book. So here, private char advance. So what does the advanced function do? Return source char at current plus plus. So this is going to take the character at the current value, the current index, and then it's going to increment current. Okay. So but this takes in one character at a time, right? So we're currently looking at a single character in this case. And so this is working fine, right? Just trying to, okay. So start is at current. I see. All right, let's go. We need an add token function. So adding a token. Well, we need another overload for the add token. This time we need the token type and the literal. For now, I think we're just doing so we could do tokens.add and new token. We need the type. We don't have a lexeme. And oh yeah, so we can get the lexeme, which is the actual value from the source because we have access to it. So what we can do is string lexeme equals to source substring. This is going to be index of the current. Is it going to be the index of the current? I think it's going to be the start. Yes, to the current, because the start is always reset to be the value of the current before we call the scan token. And then every time we advance, current is going to have been +1. So the start is going to store the current index of the lexeme and go from there too. I think that makes sense. So what we can do now is take the lexeme literal. Okay. And we also have line. So line, where is line? I have line here. Okay. What is this? Get out. Nice. So next we have to deal. Okay, let's see. The advanced method consumes the next character in the source file and returns it. Yeah, it does. Where advanced is for input, add token is for output. It grabs the text of the current lexeme and creates a new token for it. We'll use the other overload to handle tokens with literal values soon. Okay. Now, before we get too far in, let's take a moment to think about errors at the lexical level. What happens if a user throws a source file containing some character LOX doesn't use, like these, at our interpreter? Right now, those characters get silently discarded. They aren't used by the LOX language, but that doesn't mean the interpreter can pretend they aren't there. So we report an error. All right. So here we're going to move here, and the default case we're going to a LOX.error. We have a line and a message here, just like that. And the question now becomes, oh, enhanced switch. That is cool. This enhanced switch is nice. It looks really nice. This looks exactly like Kotlin, so I'm going to use this. Thank you very much, IntelliJ. Right. So we're going to print an error here, and we're gonna break. Note that the erroneous character is still consumed by the earlier call to advance. That's important so we don't get stuck in an infinite loop. Yeah, that's true, because advance is going to take the character and return it, but then the current is going to advance to the next character. So if we don't get a valid character, then the character is already consumed, and this is just going to print an error, and then we're going to continue scanning. So this is going to continue to scan whatever we need, and so we're not going to be stuck in an infinite loop as is explained here. Note also that we keep scanning. There may be other errors later in the program. It gives our users a better experience if we detect as many of those as possible in one go. Otherwise, they see one tiny error and fix it only to have the next error appear and so on. Syntax error whack-a-mole is no fun. Yeah, that's true. Don't worry, since hard error gets set, we never try to execute any of the code even though we keep going and scan the rest of it. So yes, hard error actually lives, what is this? Let's just import that. So hard error actually lives here. Where is it? Hard error actually lives here. So the moment we call error and we report the error message, then you're gonna see that hard error is going to be set, and this flag is what we can check when we're trying to do the interpretation. And if we have an error, then we've already reported all the errors, so we don't just execute any code. And here, what is this saying? It's always goodness. Anyway, operators. So now we've parsed single characters, and now we want to parse operators. So let's see. We have single character lexemes working, but that doesn't cover all of LOX's operators. What about hmm, what about exclamation mark, bang? It's a single character, right? Sometimes yes, but if the very next character is an equal sign, then we should instead create a not equals lexeme. Note that the bang and the equals are not two independent operators. you can write not space equals in locks and have it behave like an inequality operator. That's why we need to scan not equals as a single lexeme. Likewise, less than, greater than, and equal to can all be followed by equal to create the other equality and comparison operators. This is true. Oh, okay, so we have to parse them as single tokens, basically. Right. Okay, that makes sense. All right. For all of these, we need to look at the second character, right? So it's more like we're peeking into the future, right? I think that's the appropriate way to put it. We're trying to peek into the future to see the next character, and yeah, okay, cool. For all of these, we need to look at the second character. So let's just write some code. So we're gonna go back to our scanner, and here we're gonna do case bang. In this case, we're going to call add token, and we're gonna do a match on equals. And if we have a match, then we're going to do token type dot bang equal. And if we don't have a match, then we're going to just have our token type dot bang. Okay, so this makes a lot of sense. And we're gonna try to match the next character. If it does, then we get this. If not, we just get this. This is really cool. Really cool. We're gonna do the same with equals. So just gonna copy that. And this is going to be equal. This is going to be really interesting to implement in Zig, and also I think the C implementation will be fun too. All right, less than, have less than, um less yep, less equal, and this is going to be, this should be equal. Oh, okay, I'll check that out. I have no idea why that's happening. Let me know if the mic is better now. That's weird. Let's see. What the hell is going on with the mic? Ah, just going to configure set get the mic. Okay. Okay. Um, should be able to detect when the mic goes out forward. So yeah. Okay. Right. So I'm just gonna continue. Um, yeah, I think it might have something to do with the sound suppression. Yeah. Right. Okay. So I'm just gonna continue with this now. Right. So we'll do this for the less than, and we're gonna do the same for greater than, and greater equal. No, this is gonna be greater, and yeah, this is looking good. Right. Okay, so those cases use this new method. So we have the match function now, which is going to help us check. I think if this evaluates to true, then it just advances the current by 1. So let's take a look. Let's implement the match here. Boolean match. And this is a character input. Let's just call that input. Okay, expected is a better naming. It's a better name. So we're gonna do if is at end, then we're gonna return false because we didn't match anything. And then we're gonna do is source.char at the current equals expected. Then we're going to return true. Okay, we need to increment so we need to do current plus plus. If not, we're just gonna return false, right? Yeah. So in this case, you can see yeah, the implementation here is similar, right? So if it's the same, then we're gonna increment the current, and then we're gonna return true. Else, we're just gonna return the false. This guy is crazy. Anyway, yeah. So now those errors have gone away, and it's like a conditional advance. We only consume the current character if it's what we're looking for. Yep. Using match, we recognize these lexemes in 2 stages. When we reach, for example, bang, we jump to a switch case. That means we know the lexeme starts with a bang, and then we look at the next character to determine if we're on a not equals or merely just a bang. Okay. So now longer lexemes. Okay, so this is really straightforward, and I think it makes sense. So we just try to listen for a character, and where we have 2 or 3 characters tokens, then once we get the first one, we try to determine if we match with the next character, and if it is, then we're just gonna take that or not. Okay, I think this makes a lot of sense. Okay, yeah, makes a lot of sense. So we're still missing one operator slash for division. That character needs a little special handling because comments begin with a slash too. That's true. All right, so let's do it. Case slash, and actually need some, we need a block for this, right? And if we match the forward slash, then we try to check. Yeah, okay, so this is a comment basically. So and it goes on to the end of line. So while peak, we need to implement another does not equal to new line. Then we're just going to increment the just advance because we don't have anything to read. We're not doing anything with the comments, so we're just gonna strip them out. Not is at end. Cool. So while we're peaking, while we're peaking and we've not gotten a new line, and we've also not gotten to the end of the source, then we keep advancing, right? Okay. Then else, we're going to add token type dot slash. My question is, this is trying to look ahead at the next token that we haven't consumed yet, right? And this means that this loop is going to run up until the end of the line, but then it's not going to consume the new line character. Okay, we'll see. Yeah, it's not going to consume the new line character, I think. Yeah, this is similar to the other 2 character operators, except that when we find a second slash, we don't end the token yet. Instead, we keep consuming characters until we reach the end of line. This is our general strategy for handling longer lexemes. After we detect the beginning of one, we shunt over to some other Lexim specific code that keeps eating the characters until it sees the end. But we've got another helper peak here. So we need to implement this peak. This is going to be private char peak. And this is going to, we don't need, oh, we need to check is at end here too. If is at end, turn, why do we have to return this? This is like a null character, I believe. Anyway, turn source dot char at current plus one. Current. I think. Interesting. I would think that we would read. So the current character is. Oh, the current character here is one that we've actually not consumed. Okay. Actually, I think I need to look at this a bit more to understand what I'm looking at. Well, the current is always 0, right? Oh, peak does not look ahead. Peak just takes the current character and returns it. Is that what it does? I thought peak is gonna be like look into like the future, the next token, but no, that's not what we're doing. So we're just getting the current token. Yeah, all right, that's fine. Hmm. This is called look ahead. Okay, it's sort of like advanced, but it doesn't consume the character. This is called look ahead. Since it only looks at the current, yeah, okay, makes sense. Since it only looks at the current unconsumed character, we have one character of look ahead. The smaller this number is, generally, the faster the scanner runs. The rules of the lexical grammar dictates how much look ahead we need. Fortunately, most languages in wide use peak only 1 or 2 characters ahead. Comments are lexims, but they aren't meaningful and the parser doesn't want to deal with them. So when we reach the end of the comment, we don't call add token. Yeah, of course, we don't have to add the comment as a token. When we loop back around to start the next lexim, start gets reset and the comments lexim disappears in a puff of smoke. Aha, yeah, this is what I'm talking about. While we're at it, now's a good time to skip over those other meaningless characters, new lines and white space. So here, if you take a look, you see that this is where new lines are handled. So we just use that to increment the line count, and yeah, okay, that makes a lot of sense. Let's ignore some white space here. Case an empty. This is an empty. Can I just use comma separator? Case. Okay. Yeah, I think this is gonna work. T and yeah, they do nothing basically. Okay. Then we have new line. And for the new line, we're going to increment plus plus. Okay, looking good. So yes, so now the question I had regarding why we were not consuming the new line here is actually answered here. So whenever we hit the new line next, we're just going to increment the line and now we're back in. And this is how we trim white spaces in but it's gonna be interesting to see how we're going to handle strings. I think we're just gonna do strings just as we handle this, where we read the first character and then we just read up until the end. So if we're gonna read a string, I'm thinking we're just going to read the first, like, the idea that I have in my head is we're going to read a quotes and then in our net, so we're gonna like loop until we finish onto the next quotes, and that we would have read a string that way. And so yeah, all of these cases actually make a lot of sense. Let's continue. um Yeah, okay. When encountering white space, we simply go back to the beginning of the scan loop. That starts a new lexeme after the white space character. For new lines, we do the same thing, but we also increment the line counter. This is why we used peek to find the new line ending a comment instead of match. Oh yeah. So match would consume the character, but peek just returns that current character. All right. We want that new line to get us here so we can update line. Our scanner is getting smarter. It can handle fairly free from code like this. Oh, this is really cool stuff. I'm really enjoying this, to be honest. Right. String literals. Now that we're comfortable with longer lexemes, we're ready to tackle literals. We'll do strings first since they always begin with a specific character. Yes, let's do it. Let's do it. So here we're gonna do case this. Okay, we just do string. We have a string function that we're gonna call. That's okay. That calls private void string. Okay, so what does this do? This is going to peek, and we're gonna wait until we reach here, and we're not at the end. If peek line plus plus advance. Okay, yeah, I think this makes sense. So we're going to try to read until we reach here, right? And we also increment the line even. So the way I see this is our strings can be multi-line. So for example, in logs, I can probably type hello. I don't think I can type this here. Let me just open up. So I think in logs, we'll probably be able to do something like var my string is going to be equal to hello there. I am a string. And this is going to be a valid string in logs, in my opinion, because looking at the tokenization code, it's incremented the line number, but it's taking this as a valid string, which is really cool. I think I like this, to be honest. I've seen a lot of languages that, for example, Zig is going to, if you want to do multi-line strings in Zig, then you have to use this weird stuff. It's just, I don't know. I think if there is no technical like limitation, I think this approach is really cool. You know. Anyway, we'll see. Right. So let's see. So we peek, and if we peek to the new line, then we advance. Okay, makes sense. So let me just start writing my own. And so we're gonna do while we peek and it's not equal to the closing quotes, or and not is at end. We've not gotten to the end. Then we're going to, if peek is equal to a new line plus plus, and we're going to continue to advance. And let's refresh what advance does. So advance always increments the current plus plus. In this case, we don't care about the result. We care about the actual incrementing of, the counter or the current index to the string. And okay, so at the end we check have we reached the end, or we're just oh, if it's at end, then we get an unterminated string. That's true. All right, is at end box.error terminated string. Let's do line, and we get unterminated string, and we return. There's nothing to add. Advance. So this is going to take the closing quotes, because that is what is that is the current token, right? So we're going to take that, but we're not going to do anything with it, right? Here, the closing, and then we're going to trim the surrounding quotes because we've actually, yep, okay. So to trim the surrounding quotes, we're going to start from the start, add one and minus one from the current. Yeah, that makes a lot of sense. So the quotes to do string lexeme is going to be source dot substring start plus one and not end current minus one, and then we're going to add the token type string lexeme or value, what I call it. Lexeme is fine. And now I'm going to, yeah, let's continue. Like with comments, we consume characters until we hit the quotes that end the string. We also gracefully handle running out of input before the string is closed and report an error for that. For no particular reason, Log supports multi-line strings. There are pros and cons to that, but prohibiting them was a little more complex than allowing them, so I left them in. Oh. So there are pros and cons to, doing strings that way. Okay. That does mean that we need to update line when we hit a new line in a string. Okay. Finally, the interesting bit is that when we create the token, we also produce the actual string value that will be used later by the interpreter. Here, that conversion only requires a substring to strip off the surrounding quotes. If log supported escape sequences like new lines, we'd unescape those here. Yeah, so we don't support escape sequences in logs. I don't think we need to, since we are not actually constraining or restricting users um to do stuff like have strings on just one line. Yeah. Number literals. All numbers in logs are floating point at runtime, but both integer and decimal literals are supported. A number literal is a series of digital digits, optionally followed by a dot and one or more trailing digits. Okay, yeah. This is a floating point literal. This is an integer. Yeah, of course. We don't allow a leading or trailing decimal point, so these are both valid. Are both invalid. Yeah, okay. So we have these and these are not valid. We could easily support the former, but I left it out to keep things simple. The latter gets weird if we ever want to allow methods on numbers like 1 to 3 the square root. To recognize the beginning of a number lexeme, we look for any digits. It's kind of tedious to add cases for every decimal digit, so we'll stuff it in the default case instead. That's true. Okay. Doesn't switch in Java allow us to do things like is digits on the character? I would expect I'm gonna give this a shot. Is digits? Will this even work? It's gonna work. So let's just do the default case. Right. Here we're gonna do if it's digits C. Hey, Anonymous. Right. Then we're going to try to parse a number, and else we still have our error. Yep. Let's add our is digit utility private boolean digits, and then we take in the character C, and here we're going to return C is greater than or equal to 0. c is less than or equal to 9. And this will tell us if this is a valid digit. Okay. Looks cool. Now let's do the number parsing. And so to parse numbers, we're gonna do while it's digits, and we're gonna pick the current value. And so while it's digits, we're going to keep advancing. This makes a lot of sense. We're going to keep iterating over each digit, and while we're doing that, we're going to look. Oh, so when we try to parse the first digits, we might be
It's 6
parsing.
o'clock.
We might be parsing a float, right? So what is going to happen is we're going to look for a dot. Okay, that makes a lot of sense, and this is really simple. Look for fractional part. So how do we do that? We try to pick peak equals a dot, and not is at end, of course. So if peak, then we're going to continue. We're going to do this again, right? All right. Okay. So, oh, we need to consume the dots first before we start doing the number parsing again. Yeah, that makes sense. So we're going to advance on the dots, and then we're going to continue. Okay. And now at the end, we're going to add our number token. So can type number, and the value is going to be double dot parse double, and we're going to do so this the source dot substring is going to be start to current, right? Yeah. And we consume as many digits as we find for the integer part of the literal. Then we look for a fractional part, which is a decimal point followed by at least one digit. If we do have a fractional part, again, we consume as many digits as we can find. Yeah, exactly. Looking past the decimal point requires a second character of look ahead, since we don't want to consume the dot until we're sure that there is a digit after it. So we add. Oh, I see. So I think something is missing here. We pick. We're supposed to pick next, not just peak. I wasn't using that. I was using is at end. But why do we need uh uh okay, so what this is saying is when we read the current dot, we want to read past these dots to make sure that the next number we get after that is a is a real number, and if it's not, then we're not gonna bother to go into this loop at all. Okay, that makes sense. So we're not doing this. This digits pick next. Let's implement that. And so what does pick next do? It's if current plus one is greater than or equal to source dot length, then we're gonna return false, right? Nope. We're gonna return this weird no character. Okay, it's just going to be a character. And we're gonna return source dot substring char at current plus one. Okay, yeah, this is fine. I still don't understand why we have this character, why we're returning this character, but okay. We'll see. Okay, maybe because what we're trying to do is confirm that this is a digit and this is not a digit. So this might be fine. Finally, we convert the lexeme to its numeric value, right? Our interpreter uses Java's double type to represent numbers, so we produce a value of that type. We're using Java's own parsing method to convert the lexeme to a real Java double. We could implement that ourselves, but honestly, unless you're trying to cram for an upcoming programming interview, it's not worth your time. The remaining literals are booleans and nil, but we'll handle those as keywords, which gets us to reserved words and identifiers. Okay. Our scanner is almost done. The only remaining pieces of the lexical grammar to implement are identifiers and their close cousins, the reserved words. So we're getting into the territory of reserved words and identifiers. Okay. You might think we could match keywords like or in the same way we handle multiple character operators like this and uh consider what would happen if a user named a variable orchid. The character would see the first two letters or and immediately emit an or keyword token. Oh my god, that would be bad. This gets us to an important principle called maximum match. When two lexical grammar rules can both match a chunk of code that the scanner is looking at, whichever one matches the most characters wins. That rule states that if we can match orchid as an identifier and or as a keyword, then the former wins. This is also why we tacitly assumed previously that less equals should be scanned as a single less equals token and not less than followed by equals. Okay. Maximum match means that we can easily detect a reserved word until we've reached the end of what might instead be an identifier. After all, a reserved word is an identifier. It's just one that has been cleaned by the language for its own use. True. That's where the term reserved word comes from. So we begin by assuming any lexeme starting with a letter or underscore is an identifier. So in the default case, we have else if is alpha, and we try to parse an identifier. And so this is where, so once the identifier is fully parsed, we can then compare that value to one of the two reserved words, basically. I think that makes sense. Okay, so let's get back to our big switch statement. And here we're going to do else if is alpha. This is going to be the character. It's in there. Identifier. Yep. And here, okay, we have the identifier. And let's go implement that. Private void identifier. And here we're going to say, well, is alpha numeric, right? Yep. This is going to pick this. Okay, I think this is it. I'm going to see. When I turn. Right. Okay. Well. Okay, I think this is good. Right. So here, what are we doing? Oh yeah, so we're doing advanced while this is alphanumeric. So if we keep getting like alphanumeric characters which conforms to what an identifier should be, then we keep advancing. And then we're just going to add the token and this token type dot identifier. The question for me is we keep parsing until, so we've already parsed before we call this function. We were already able to parse an alpha character, right? So we just continue to read until we get to the end of a valid identifier. So that means we could hit like some operator character, or we could hit we could hit an operator, or we could hit a space and something that is not alphanumeric, and that would terminate this identifier. So for example, we could do something like var name equals Samuel. And so if you're trying to parse this var, then the first thing we'll do is pass v, and then we're gonna hit this identifier function, and then we're gonna pass var, the ar, because that this is alphanumeric. But the next character after that, which is this space, is not alphanumeric, so this is going to break, and we're gonna be able to get just this as the identifier. Now, I was thinking of an extreme case where we don't have spaces between the characters, and so we have something like this, right? And name is still going to be parsed correctly because remember, this is just alphanumeric. And so when we hit equals, this is not a part of the identifier, so this is going to be parsed, and we're going to be left with this. Okay, this is really cool stuff. Wow. I'm really learning a lot from this book, and yeah, really cool. Right. So we add the identifier token. Yep. So let's implement the helpers is alpha and is alphanumeric. Private boolean is alpha. Char C. And okay, this is return C is greater than or equal to A, and C is less than or equal to Z, right? Or C is greater than or equal to A, and C is less than or equal to Z, or C is greater than or equal to, oh, this is just alpha, right? So this is fine. And we could do is alphanumeric, and we just have an or. C is greater than or equal to 0, and C is less than or equal to 9. I think this is it, right? Or we could just use this, right? Okay, we could also compare underscores. Let's do the underscore comparison, or C equals to underscore. So underscore is a supported thing, and yeah, let's use the helper functions. Is alpha C or is digit C? Nice, really nice. Looking good, really looking good. Okay, so that gets identifiers working, as we've seen. To handle keywords, we see if the identifier's lexeme is one of the reserved words. If so, we use a token type specific to that keyword. We define this set of reserved words in a map. Okay. So we're gonna have to store that here. Static final what? Map string token type keywords. In the static block, we're going to do keywords keywords equals to a hash map of string token type, and here we go. What equals to a new hash map, obviously. Yeah, we don't even need these things, right? And then we can start adding them. So we have and, else, whatever. I'm not going to type all of these. I think I should just copy and paste them. And we can do let me see, what is the best way to do this? Yep. I think this is fine. I need to remove spaces. Weird. Okay, I think, yeah. Ooh. Okay, this looks good. Return this true var and var. So this hash map is going to have all of the keywords, and we can compare the keys. We can try to get, so whenever we try to, so we can use the identifier we're getting here to actually we compare that to the words in the reserved words in the hash map, and if the key matches one of these, then we know that we have the token for that particular reserved or keyword. Okay, so then we can then after we scan an identifier, we check to see if it matches anything in the map. So while it's alphanumeric pig advance, okay, so let's go back to the identifier. Here we're going to do string text, which is a text dot, so source dot substring, and this is going to be the start to the current. And now we need to check if this text is inside of the hash map, is the key basically. So token type equals to keywords that get the text, right? So this is going to tell us whether we have this keyword here. So this is the key, and if it matches, then we should get a valid token type, right? In this case, if type is null, type is going to equal token type dot identifier, and we're going to add that as the type here. Ah, goodness. Right, my plan is to finish this, but we're still doing like tokenization. We've not even gotten to the parsing stage yet. Oh my goodness, this is gonna be very long. Right. Stream has gone for like 2 hours already. Okay. Right. Yes, if so, we use that keyword token type. Otherwise, it's a regular defined identifier. And with that, we now have a complete scanner for the entire Lux lexical grammar. Fire up the REPL and type in some valid and invalid code. Does it produce the tokens you expect? Try to come up with some interesting edge cases and see if it handles them as it should. Okay, so it looks like we're done with this chapter and we can continue. Yeah, of course we could read this, but this is really gonna take some time. So let's just go to representing code. But before we do that, I would like to run the code just so we see. We've been writing code for a while and we haven't run it yet, so let's just do that now. And let's go to Lux and the main method and run it. Okay, waiting for this to finish. Waiting patiently. Oh, we've been waiting, but it's running already. So what I could do is something like var name equals Adebayo semicolon, and I hit this. And what do I get? I get a token, and the token type is of var. This is the text, and this is the value. This is the literal. We don't have a literal here, and you can see we also have an identifier we have a name and we have no. So this is actually parsing this quite well. Wow. So we parse in a var, as you can see here. We also get an identifier, which is name, as you can see, name, and we have the equal, which is this, and then a string. And this is the string. We have a semicolon here. And so it looks like our tokenizer is working really well. So yeah, nice work. And so I'm going to take like a 5 minutes break, just to cool off a bit, and then we're gonna continue. Yep, we're going to continue. I really want to finish this, so yeah. And I need to type this somewhere. Let me just open up VS Code and cool. And I need to switch to that. Where is it? VS Code. Oh, okay. Yeah, that's fine. Damn. Okay, I think it's time to continue. So, let's see. I hope I'm still audible. Cool. Don't save. Let's continue. So yes, representing code. In the last chapter, we took the raw source code as a string and transformed it into a slightly higher level representation, a series of tokens. The parser we'll write in the next chapter takes these tokens and transforms them yet again into an even richer, more complex representation. Before we can produce that representation, we need to define it, right? That's the subject of this chapter. Along the way, we'll cover some theory around formal grammar, feel the difference between functional and object-oriented programming, go over a couple of design patterns, and do some metaprogramming. Okay, metaprogramming, let's go. Before we do all that, let's focus on the main goal, a representation for code. It should be simple for the parser to produce and easy for the interpreter to consume. If you haven't written a parser or interpreter yet, those requirements aren't exactly illuminating. Maybe your intuition can help. What is your brain doing when you play the part of a human interpreter? How do you mentally evaluate an arithmetic expression like this? 1 plus 2 times 3 minus 4. Because you understand the other operations, the old please excuse my dear Auntie Sally stuff. You know that the multiplication is evaluated before the addition or subtraction. One way to visualize that precedence is using a tree. Leaf nodes are numbers, and interior nodes are operators with branches for each of the operands. In order to evaluate an arithmetic node, you need to know the numeric values of its subtrees, so you have to evaluate those first. That means working your way from the leaves up to the root, a post-order traversal. Okay, so we have this. You walk your way from here, from the leaf node all the way to the root node. Okay, we'll see. If I gave you an arithmetic expression, you could draw one of these trees pretty easily. Given a tree, you can evaluate it without breaking a sweat. So it intuitively seems like a workable representation of our code is a tree that matches the grammatical structure, the operator nesting of the language. We need to get more precise about what grammar is then, like the logical grammars, blah 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 blah. Let's just move on. Context-free grammars, really. Rules for grammars. Okay, so this is talking about we're trying to build like this grammar for the language, and yeah, this makes sense. So let's just take a look at the grammar for our own language. I don't think we should spend time trying to read this. I think they're gonna be using like this backwards nor form or whatever. So yes, I think I understand what this is doing or what this is saying here. So for this grammar, we have an expression, and an expression is made up of a literal or a unary, binary, or grouping expression. Then we're going to define what literal expression is. So a literal is made up of a number or a string, or the string true, false, or nil. So these are the valid literals for this particular programming language, right? We could also talk about the unary, and unary is made up of this hyphen, which is the negation operator, or a bang. This is a minus operator, right? And we also have this bang, which is a negation operator, and we could also have an expression. So you can see this is where we have this like we have this thing where it's like recursive and it can contain one another, that kind of stuff. And so because this now has this, and it's just something that is appended or prepended for an expression, and then we have a semicolon at the end. Yeah, so that's pretty much it. And we have binary, so this is going to be an expression, an operator, and an expression. And now we have to specify what an operator is, and you can see an operator is either equals, not equals, less than, this. So we have all of these things. These are the valid operators of the language. And yeah, okay, we also have grouping, and you can see grouping is just a
open brace followed by the expression and a closing brace. So this is just defining the grammar for the language, right? It's basically telling us, oh, this is how the language is supposed to work, right? In addition to quota strings for terminals that match exact lexemes, we capitalize terminals that are a single lexeme which text representation may vary. Number is any number literal and string is any string literal. Later, we do the same for identifier. This grammar is actually ambiguous, which we'll see when we get to parsing it, but it's good enough now. Okay, let's do syntax trees. Finally, we get to write some code. That little expression grammar is our skeleton. Since the grammar is recursive, note how grouping, unary, and binary all refer back to expression exactly. Our data structure will form a tree. Since this structure represents the syntax of our language, it's called a syntax tree. Our scanner used a single token class to represent all kinds of lexemes. To distinguish the different kinds, think the number 123 versus the string 123. We include a simple token type enum. Syntax trees are not so homogeneous. Unary expressions have a single operand, binary expressions have 2, and literals have 0. Yeah, okay. That makes sense. We could merge that all together into a single expression class with arbitrary lists of children. Trying to the hell. Okay. Right. This is weird. Okay. Where was I? We could merge together. Okay, some compilers do. Yeah, we could merge that all together into a single expression class with an arbitrary list of children. Some compilers do, but I like getting most out of Java's type system, so we'll define a base class for expressions. Then for each kind of expression, each production under expression, we create a subclass that has fields for the non-terminal specific to that rule. That way, we get a compile error if we say try to access the second operand of a unary expression. Yeah, because it doesn't exist. Yeah, okay. Something like this. So we have an abstract class called expression, and we have a static class binary, which is going to extend expression, and a binary expression is we have left, we have the operator, and then we have the right expression. Okay, this is really cool. And so yeah, we know because we have the Java type system to rely on, then we can properly specify what kind of expressions that we need to take care of for this AST. Okay, expression is the base class, or I'm just gonna say expression. Expression is the base class that all expression classes inherit from. As you can see from binary, the subclasses are nested inside of it. There is no technical need for these, but it lets us cram all of our classes into a single Java file. Disoriented objects. You note that much like the token class, there aren't any methods here. It's a dump structure. Nicely typed, but merely a bag of data. This feels strange in an object-oriented language like Java. Shouldn't the class do stuff? The problem is that these tree classes aren't owned by any single domain. Should they have methods for parsing since that's where trees are created, or interpreting since that's where they are consumed? Trees span the border between those territories, which means they are really owned by neither. In fact, these types exist to enable the parser and interpreter to communicate. That lends itself to types that are simply data with no associated behavior. This style is very natural in functional languages like Lisp and ML, where all data is separate from behavior, but it feels odd in Java. Okay. Functional programming aficionados right now are jumping up and exclaiming, see, object-oriented languages are a bad fit for an interpreter. I won't go that far. You recall that the scanner itself was admirably suited to object orientation. it had all the mutable state to keep track of where it was in source code, a well-defined set of public methods, and a handful of private helpers. My feeling is that each phase or part of the interpreter work finds for an object-oriented language. It is the data structure that flows between them that are stripped of behavior. So let's meta program the trees. Java can express behaviorless classes, but I wouldn't say that it's particularly great at it. 11 lines of code to stuff 3 fields in an object is pretty tedious, and when we're all done, we're gonna have 21 of these classes. Yeah, I think Java is just verbose by default, and that's one of the major issues with the language. Well, yeah. I don't want to waste your time on my ink writing all that down. Really, what is the essence of each subclass? A name, a list of typed fields. That's it. We're smart language hackers, right? Let's automate. Let's automate. Oh, we're gonna automate. Okay. Instead of tediously handwriting each class definition, field declaration, constructor, and initializer, we'll hack together a script that does it for us. It has a description of each tree type, its name and fields. It prints out the Java code needed to define a class with that name and state. This script is a tiny Java command line app that generates a file named expert.java. Wow, so we're going to be doing some meta programming. We want to do some utility stuff. All right, let's do it. So we're going to create a new package here. And the package is going to be tooling, because this is going to be different from the actual compiler program. This is going to be helping us generate classes. So we have this class called generate AST. Okay, let's do it. Generate AST. Okay. Yeah, I'm just going to capitalize the AST. Right. And the main function, we're going to make sure to, let's throw our IO exception as is thrown in the book. Then we're going to do if args.length does not equal to 1. Is that what it is? Yep. So we want one argument, and system.error.println, and we're gonna do usage generate AST output directory. Okay, and system.exits with 64. Now this is looking good. So output directory is going to be args at 0. So this is giving us the output directory. Remember, we checked this here already. Now looking good. Note that this file is in a different package, .tool instead of .logs. This script isn't part of the interpreter itself. It's a tool we, the people hacking on the interpreter, run ourselves to generate the syntax tree classes. When it's done, we treat expert.java like any other file in the implementation. We are merely automating how that file gets altered. To generate the class, it needs to have some description of each type and its fields. Okay. So we're going to do define AST, right? Output directory, which is where we're gonna store everything, and the class name is probably gonna be xpr arrays.asList. This is really cool. I love this. And here we're going to have binary. Binary is going to be okay. Let's just have it. Okay, I'm going to have xper left token operator xper right. Okay, so this is going to construct. This is just a utility to construct. We're gonna parse this, and then we're gonna construct. We're gonna construct subclasses of xper. Really interesting stuff. Okay. Then we're gonna do. Okay. Grouping. and this is going to be expr expression and nope, literal. And for literal, we're gonna have object value. Here we're gonna have unary operator, which is just a is this gonna be an expression? No, just a token. And then we're gonna have expr, right? Yeah. So for now, we're going to, yeah, so it says, for brevity's sake, I jammed the descriptions of the expression types into strings. Each is the name of the class followed by colon and the list of fields separated by commas. Each field has a type and a name. The first thing define.ast needs to do is output the base expr class. Private static void define.ast, so let's do that. So define.ast takes in a string output directory and a list of string, which is going to be we have string base name. Yeah, we have string base name, and then we have a list of string for the types that we're generating, right? Really cool stuff, really cool. Right. And this is going to throw IO exception. This is going to throw IO exception. And so now we're going to do string path equals output directory. What are we trying to do here? Plus slash base name Java. Okay. Okay, let's go. So this is output directory plus slash plus base name plus the Java. In this case, this is going to be expr.java, and then we're gonna make ourselves a print writer. Writer equals new print writer. The path, and this is the char set. Can I get access to the char set for name? UTF-8, I believe. What is this? Okay, nice. Writer.println. This is going to be package. In this case, it's com.biocode. And yeah, this is where we need to, this is the package description we need to add. Wow, so this is classic Java code generation. Really cool. And then we're gonna print an empty new line, and then we're going to write. Okay, we're just gonna print line again. Import java.util.list, and we're gonna do another print line, and then we're gonna have an abstract class. Base name in this case is going to be expr. Base name, open the brace, and we're gonna close this, and writer the close. So what we just did is we just generated a class that has nothing in it for now. Okay, that's progress. That is progress. Right. Okay. When we call this base name is expr, which is both the name of the class and the name of the file it outputs. Okay. we pass this as an argument instead of hard coding the name because we'll add a separate family of classes later for statements. Inside the base class, we define each subclass, right? So we're gonna continue the AST classes basically. So we have to loop through each of those subclasses. So here, inside of the parenthesis, we're going to loop through this for string type. In types, what do we want to do? We want to generate stuff, so we have to start splitting stuff first. For me, okay, let me just take a look at this. Right, so we have binary, and then we have this. Right, so for me, what I would do is I have to split everything, right? So I'm gonna do final list of string types of values, and it's going to be type.split everything with a colon, possibly yeah, this should give me a list. Oh, this just gives me a string array. This is fine. I'm going to split this, and then what we're gonna do is, okay, this is it, and we have the class name. So class name is going to be values at 0.trim, and then the fields is going to be values at 1.trim again, and then we can define the type. So define type is going to be for the writer. We're gonna specify the base name, the class name, and the fields, and off we go to implement define type. So we're going to do private static void define type and print writer string base name, string class name, and string field list. Okay, field list is fine. Writer the print line. What do we have? Static class, the base class name, I believe. Yeah, extends base name, and we have our opening brace. And let's do some constructor, and the constructor is going to be writer the print line, right, plus class name plus opening brace plus field list plus closing brace plus space and an opening brace. Yep. Oh, I could just do this here, right? Yep. Okay. Looking good. What is this? Store parameters in fields. So we have fields, and I have to split this now. So string fields equal to equals to field list dot split comma. These are comma separated. Okay. So these are comma separated, and we just split these, and now we can do for string field in fields. Okay, I'm not gonna lie. This is making me feel like it's making me rethink how, code generation, how useful code generation could be. And it's not even a difficult thing to do because, well, okay, I I think in some languages like Kotlin, for example, this would probably be easier to do. So I'm really liking this, to be honest. This is really cool stuff. I, yeah. So for this field, we're going to have to split it again. Yeah, because we have something like this. So we have already split these, and now we're gonna split this and this. Okay, let's do it. Let's do it. Let's do it. String name equals to field or split space at 1. So we're getting the name of the field, right? We're getting the name of the field. And so what we're gonna do with that is writer the print line. In this case, 1, 2, 3, 4, 5, 6, 7, 8. Right? We're also gonna do plus. Okay. This dots name equals name semicolon. Yep, that's what we need. And then we're gonna print line again. Except here we need to do 1, 2, 3, 4. Yep. All right. Looking good. So no, this should not be done here. This should be done here. Right. There we go. All of that glorious Java boilerplate is done. It declares each field in the class body. It defines wait in the class body. Where is it? No, we just did constructor. We don't declare anything in the class body. Did I miss that? I think I did. Holy shit. I missed it. No, I didn't. I didn't. I just didn't do this. Okay, let's do it then. Let's do it. Let's do it. Writer dot print line. Right. We're gonna do that. And now we're gonna declare the fields, right? So it's just the same as this. We're gonna iterate over each field, but now we're going to split this because we're gonna have string array names, field value something, whatever. And then the no, we don't need to do this, right? We can just take the field and we specify for, yep, and the name is just the field, right? So we take that field and then we put a semicolon here, and this should work. So we have the field. Do we not want private? Is that, yeah, I think we might want to do private like this or something. Oh, final. Okay, we don't want private, we want final. And then we have the field and we have a semicolon at the end. Exactly. Right. And then we print the end of the class. So let me just make sure we have a static class that extends this. We specify the constructor. We specify the field list inside of the constructor, and we close that constructor off. And now we are specifying the variables in the field, and so now we need to close the actual class. So here we go. Nice one. And there we go. All of that glorious Java boilerplate is done. It declares each field in the class body. It defines the constructor for the class with parameters for each field and initializes them in the body. Compile and run this Java program now, and it blasts out a new.java file containing a few dozen lines of code. That file is about to get even longer. Honestly, imagine that we didn't write like this 67 lines of code generation, and we have to like manually write all of these things. Anyway, let's see, what do we have here? So let's just try to execute this and see what we get. We need to pass in something, right? So I need to modify the wrong configuration for this because I need to pass in an argument. So the program argument is going to be here. And let me just confirm something. I have no idea. Okay, I'm just going to see if I can jlox source main java. You know what? I'm just going to copy the path for this, if I can find it. Yeah, just okay. Copy path or reference. Absolute path is fine. And so here I'm going to modify the wrong configuration. Program argument is going to be this folder. And yeah, this is what I want. And so I'm gonna apply and do OK. And now I'm gonna run generate AST. And let's wait for that to finish. 3 hours, damn. Okay, this is done. And it has spit out an exported Java file. Cool stuff. Interestingly enough, let's open this up. And we have a few issues, which is fine. We can fix it. I mean, we should specify that this class is auto-generated, you know. What is this? I'm trying to figure out why we have binary expression here. Oh yeah, this is fine. Static class binary expression. I'm just trying to figure out this dot token. This dot expression is an expression. No, this is wrong. So let's go back to our generate AST and see what we did wrong here. So here we have a static class, okay, and extends whatever. This is looking good. However, we have class name field list. What is going on? Extends expression. And then we're supposed to have, yes, we have everything as we expect, but where we have this dot something, so why is this let me just check. Token operator. Well, we'll split the colon, right? Which is what we did here, and then we get the 0 value. Oh, then we do the define type for field 1, which is for the fields. That's fine. And for the fields, we split them here, and this is supposed to be space separated, and that's exactly what it is. We get name, index 1 down. This is the second value, right? No, let's take this one. So we have this. We split this, and this should be the index 1, but apparently something went wrong here. I'm gonna have to do some print debugging. So let's do it. Let's see, what do we need to do that here, right? Print line field. That's the first thing we have to run. Field. Oh yeah, we need to delete expert.java because yeah, we didn't generate it correctly. So let's take a look. Yeah, so we have field, expert left, token operator. Oh, I see. We're supposed to at least do some trimming, right? So we didn't trim anything. Oh, I did trim here.
It's 7.
Okay. And here we have the field, and oh yeah, we split this, right? So we're supposed to probably do field.trim, and before we split it, so I'm gonna do field.trim.split by space, and I'm even gonna trim this too just because I'm paranoid. And yeah, I'm gonna delete this again, and then I'm gonna check this again. So abstract class, forget the space, Java, open and brace. We have our static class, extends base name, open and brace. Then we have the field list, which is fine. Let's just run this and see what we generated. That way we can have some eyes. And you can see, okay, this is looking better. So now we have our static class binary expression. We have binary expression here. We have all the fields. We have grouping expression. Oh yeah, so this is wrong. Like the way we do indentation here is wrong. I need to fix that. So static class, whatever. And yeah, so this is going to the next line. Then we have this thing, which is fine. No, it's not. I need 4 extra lines here, and because of that I need 4 extra lines here. Yes, and because of that I need 4 extra lines here, 4 extra lines here, 8 extra lines here. I think that is it, right? So I'm gonna delete this again, and let's see, what do we generate this time? Oh, we generate the correct thing. Okay, this is too much. We just needed to do 4. All right. Let's delete this again. Regenerate the code, and now we have our abstract class expert. We have our binary expression, and looking good. Operator left, right, looking good. We have our grouping expression. We have our literal expression. We have our unary expression. Yes, this is looking as good as we might expect. We have some spacing things, some issues with spacing and all going on here. I think it's just a matter of trimming these things properly, and yep, yeah, this has been trimmed. Yeah, okay. I think that is it. One last thing, we need to put a space here. All right, so we need to stop nitpicking about irrelevant stuff and get back into this. So this is working now, and we can actually use this, but I'm going to delete this one more time and regenerate it. And now here you can see that we have something that is Not bad to look at, to be honest. Let's go. Now, blast a new Java file. Yeah, that's true. We're doing well. So working with trees. Put on your imagination hat for a moment. Even though we aren't there yet, consider what the interpreter would do with the syntax trees. Each kind of expression in logs behaves differently at runtime. This means that the interpreter needs to select a different chunk of code to handle each expression type. With tokens, we can simply switch on the token type, but we don't have a type enum for the syntax trees, just a separate Java class for each one. We could write a long chain of type tests, so if instance of this, that, but all those sequential type tests are slow. Expression types whose names are alphabetically later will take longer to execute because they will fall through more if cases before finding the right type. That's not my idea of an elegant solution. We have a family of classes and we need to associate a chunk of behavior with each one. The natural solution in an object-oriented language like Java is to push those behaviors into methods on the class themselves. We could add an abstract interpret function method on expr, which each subclass will then implement to interpret itself. This works alright for tiny projects, but it scales poorly. Like I noted before, these three classes span a few domains. At the very least, both the parser and interpreter will mess with them. As you see later, we need to do name resolution on them. If our language was statically typed, we'd have a type checking pass. Okay. This exact thing is literally called interpreter pattern, design patterns, blah, 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 blah. This works alright for tiny projects, but it scales poorly. Like I noted before, these three classes span a few domains. At the very least, both the parser and interpreter will mess with them. Yeah, of course, we've read this before. If we added instance methods to the expression classes for every one of those operators, that will smush out a bunch of different domains together. That violates separation of concerns and lead to how to maintain code. The expression problem. This problem is more fundamental than it may seem at first. We have a handful of types and a handful of high-level operations like interpret. For each pair of type and operation, we need a specific implementation. Picture a table. Okay. So we have interpret, resolve, and analyze for each of them. Rows are types and columns are operations. Each cell represents the unique piece of code to implement the operation on that type. An object-oriented language like Java assumes that all of the code in one row naturally hangs together. It figures all the things you do with a type are likely related to each other, and the language makes it easy to define them together as methods inside the same class. This makes it easy to extend the table by adding new rows. Simply define a new class. Yeah, that's true. No existing code has to be touched, but imagine if you want to add a new operation, a new column. In Java, that means cracking open each of those existing classes and adding a method to it. Functional paradigm language in the ML family flip that around. There, you don't have classes with methods. Types and functions are totally distinct. To implement an operation for a number of different types, you would define a single function. In the body of that function, you use pattern matching instead of a type-based switch on steroids to implement the operation for each type, all in one place. Interesting. Okay. This makes it trivial to add new operations. Simply define the function that pattern matches on all of the types. Let's keep going. But conversely, adding a new type is hard. You have to go back and add a new case to all the pattern matching in all of the existing functions. Each style has certain grain to it. That's what the paradigm name literally says. An object-oriented language wants you to orient your code along the rows of types. A functional language instead encourages you to lump each column's worth of code together into a function. A bunch of smart language nerds noticed that neither style made it easy to add both rows and columns to the table. They call this difficulty the expression problem because, like we are now, they first ran into it when they were trying to figure out the best way to model expression syntax tree nodes in a compiler. People have thrown all sorts of language features, design patterns, and programming tricks to try and knock that problem down, but no perfect language has finished it off yet. In the meantime, the best we can do is try to pick a language which orientation matches the natural architecture seams in the program we're writing. Object orientation works fine for many parts of our interpreter, but these three classes rub against the grain of Java. Fortunately, there's a design pattern we can bring to bear on it: the visitor pattern. Visitor pattern. The visitor pattern is the most widely misunderstood pattern in all of design patterns, which is really saying something when you look at the software architecture excesses in the past couple of decades. The trouble starts with the terminology. The pattern isn't about visiting. The accept method in it doesn't conjure up any helpful imagery either. Many think that the pattern has to do with traversing trees, which isn't the case at all. We're going to use it on a set of classes that are tree-like, but that's a coincidence. As you see, the pattern works as well on a single object. The visitor pattern is really about approximating the functional style within an OOP language. It lets us add new columns to that table easily. We can define all of the behaviors for a new operation and set of types in one place without having to touch the types themselves. It does this the same way we solve almost every problem in computer science, by adding on a layer of indirection. Okay, makes sense. Before we apply it to our AutoGenerator expert classes, let's walk through a simpler example. Say we have two kinds of pastries, bayonets and crawlers. Okay, we have pastry, we have this that extends pastry. We want to be able to define a new pastry operations, cooking them, eating them, decorating them without having to add a new method to each class every time. Here's how we do it. We define a separate interface, okay, pastry visitor, and we can visit bayonet, visit crawler. Each operation that can be performed on pastries is a new class that implements that interface. It has a concrete method for each type of pastry that keeps the code for the operation on both types all nested snugly together in one class. Given some pastry, how do we route it to the correct method on the visitor based on its type? Polymorphism to the rescue. We add this method to pastry. Okay, so the pastry is going to accept a pastry visitor. Interesting. So each subclass implements it. Okay, interesting. All right, let's go. Each subclass implements it, and okay. To perform an operation on a pastry, we call its accept method and pass in the visitor for the operation we want to execute. The specific subclass overriding implementation of accept turns around and calls the appropriate visitor method of the visitor and passes itself to it. That's the heart of the trick right there. It lets us use polymorphic dispatch on the pastry classes to select the appropriate method on the visitor class. In the table, each pastry class is a row, but if you look at all the methods for a single visitor, they form a column. Okay, I think I'm understanding this. The visitor pattern is... Okay, let's just keep going. We added one accept method to each class, and we can use it for as many visitors as we want without having to touch the pastry classes again. It's a clever pattern. Visitor for expressions. Okay, let's read it into the expression classes. We'll also refine the pattern a little. In the pastry example, the visitor and accept methods don't return anything. In practice, visitors often want to define operations that produce values. But what return type should accept have? We can't assume every visitor class wants to produce the same type, so we'll use generics to let each implementation fill in a return type. First, we define the visitor interface. Again, we nest it inside the base class so that we keep everything in one file. Okay, so we're going back to our generator class. That's interesting. So here where we defined the actual AST class. So where is it? Yeah, here. We're going to continue by defining a vision, 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 a a vision 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 a